Good day, everyone. I am Engineer Joshua Roco, and I'll be presenting our paper, which I co-authored with Dr. Michael Angelo from Promentilla, entitled Philippine Energy Network Design via P-graph and Analytic Hierarchy. Now, let me start with Ambition Natin 2040, which is a collective long-term vision of the Filipino people in the next 25 years. Its aim is for Filipinos to have a matatag, maginhawa, at panatag na buhay. And one foundation of Ambition Natin 2040 is the energy sector, which needs to provide affordable and secure energy. Hence, the Department of Energy has recently developed the Philippine Energy Plan, which spans from 2018 to 2040. And its goals include increasing the production of clean and indigenous sources of energy, decreasing energy waste, and ensuring the balance between reliability, affordability, economic growth, and environmental protection. Now, let us look at the energy scenario here in the Philippines. This is the Sankey diagram, which in simple terms, you can take it as the overall energy balance of the country. And in 2018, majority of our primary energy supply still comes from coal and oil, which are mostly important, garnering a energy self-sufficiency of 50%, while natural gas and renewable energy dominate our indigenous energy supply at 80%. Now, the energy plan projects the outlook on energy demand and supply chain that is simulated using two scenarios: the reference scenario and the clean energy scenario. The reference scenario projects energy supply chain using business as usual strategies, while the clean energy scenario introduces innovations, major investments, and policy shifts. Now, P-graph is a tool used for process network synthesis that has been used for urban metabolism design and mostly in energy planning, while AHP is a multiple criteria decision analysis that integrates the inherent subjectivity of decisions into a mathematical framework. And together, P-graph and AHP have the potential to improve the sustainability of the energy supply networks. Thus, through an integrated P-graph and AHP framework, the overall objective of the study was to redesign the 2020 Philippine energy flow to come up with a sustainable energy supply network. And its specific objectives include identification of the most near optimal supply networks using the sustainability indicators such as low global warming potential, overall cost, electricity costs, and high job generations and energy self-sufficiency, and comparison of these optimal networks through AHP, where the weights of criteria will be derived from experts in the field of energy, planning, industry practitioners, and sustainability engineering. Now, let me start with the results of the AHP. AHP was used to generate the relative weights of the sustainability indicators. And the relative weights were used to generate a sustainability score when the indicators are combined. Here summarizes the respondents' profile. We have 18 respondents. We had 18 respondents, 42 years old average age, and 16 years average years of experience. Respondents came from a wide range of experts, from the academe, energy sector, EHS, and manufacturing. And this balanced the weights from both the perspective of the energy producers, the planners, the analysts, and the end users. And these are the result of the AHP. Among the sustainability criteria, the respondents overall gave energy self-sufficiency as it's the highest importance and the capex with the lowest importance, while the rest having the same or approximately equal weights. AHP resulted with a good 1% consistency ratio. But interestingly, AHP showed the important sustainability criteria for each subgroup. For instance, Energy users gave importance on jobs generated and electricity cost, while EHS and manufacturing practitioners gave energy self-sufficiency as the highest with the highest importance, while the academe gave importance to global warming potential. The results gave a glimpse on how energy producers, analysts, consumers define energy sustainability in their respective fields. The results encourage multi-sectoral discussion when conducting energy planning. Now, with the AHP weights derived, we now proceed with the P-graph framework. The energy Sankey was modified to be used as the basis of the maximal structure. Energy transformation ratios in 2020 were approximated using the Sankey in 2019. And it is assumed that the indigenous materials are free, there are no existing facilities, and we have an unlimited renewable resources. Now, for the outputs, we have the sustainability indicators, CAPEX, jobs generated, global warming potential, self-sufficiency, and electricity cost. And the P-graph is subjected into constraints such as the minimum jobs required, maximum global warming potential, maximum electricity cost, and the required energy consumption as indicated in the reference in the clean energy standards. Here is the maximal structure. It is composed of 3 parts. Each power plant is connected to 5 nodes. Its source, electricity generation, and sustainability indicators including job generation, global warming potential, and electricity cost. The energy supplies were divided into renewable and non-renewable, and the demand were divided into electricity and non-electricity energy demands. Of course, the numerical values of each component and their resulting ratios were derived from the 2019 Philippine energy flows. And here are the results of the P-graph simulation with the AHP sustainability indicator weights. For simplification, we only analyzed 1 optimal and 9 suboptimal networks. And interestingly, 6 out of 10 of the optimal networks came from the reference scenario. The main reason was that the high energy or the high electricity cost or the price of electricity was there for the clean energy scenario. But on the average, the top 10 networks gave 14% lower electricity cost, 51% lower global warming potential, 63% higher jobs generated, 88% lower capital expense, and 95% higher energy self-sufficiency. And here are the summary of the materials, products, and infrastructures used per solution. As you can see, only renewable energies were considered for the electricity use. But coal, oil, and natural gas, and biomass were still part of the energy system because of their non-electricity energy demands. All of the oil, coal extraction, and imports were used for oil products and coal use. Now, the extracted natural gas were all used in the oil refining. And finally, biofuels were not considered in the oil product use network because of its high capex cost. So we have for the electricity use the renewable sources such as geo, hydro, and solar energy sources. And with that simulations, we found out some P-graph limitations. One is that the ranking of the energy mix cannot be altered because the reference energy flows already have a preset energy mix. So, for instance, as you can see in the as you have seen in the infrastructures earlier, the wind and the solar were seldomly used, but they have the least capex and they produce the least global warming potential and have the highest energy self-sufficiency. But because of not only is their electricity cost significantly higher than the others, but also the reference Sankey diagram already had them rank the least energy shares at 0.6%. Next, given the similar restrictions, the P-graph cannot be used to simulate future energy mix such as in 2040 due to failure to account nonlinear effects, time periods, and it yields risk of high dimensionality. For instance, even if the energy supply and demand were scaled to 2040, maintaining the energy conversion ratios would fail to generate solutions. The ratios would blow up because they are assumed linear. Now, our recommendation is that planning for future energy mix using P-graph would require updating the energy demand and supply, as well as projecting the energy flow ratios. And here is the optimal solution based on all the simulations. The optimal network generated 52% lower global warming potential, 2% higher jobs generated, 27% lower price of electricity, 87% capex, and lower capex, and 78% higher energy self-sufficiency. And like its suboptimal solutions, the optimal Philippine energy network is composed of the following: 100% energy or electricity comes from renewable energy, and oil, coal, and biomass without biofuels energy supplies were directed to meet the non-electricity energy demands. In conclusion, our study used P-graph and AHP in the design of sustainable energy supply network in the Philippines. The sustainability score was defined through AHP with objectives of having low global warming potential, low capex, low electricity costs, and high job generations, and high energy self-sufficiency. AHP showed that generally energy self-sufficiency was the most prioritized sustainability criteria, and the variations emphasized the need for multi-sectoral approach. In the P-graph simulation, it was constructed under assumptions arising from, of course, data limitations and the simplicity of analysis. We have seen the simulation, the limitations of P-graph in energy planning, mainly due to P-graph's mixed integer linear programming nature. Meaning, projecting the energy supply and demand would also require projecting energy flows to prevent blowing up the ratios, because scaling functions were assumed linear, which deviated the solutions from actual scenarios. And energy mix solutions were limited to reference flow scenarios. Nonetheless, the optimal energy and near optimal solutions showed that the sustainable energy supply network relied on renewable energy for electricity use while maintaining other energy sources such as coal, oil, natural gas, and biomass for non-energy demands. And with that, I end my presentation. Thank you.